Good morning, everyone. Welcome to the Easy Power four-part series on Introduction to Protective Device Coordination. My name is Jim Chastain. I'm a solutions engineer, and the solution we're focusing on today is Easy Power capabilities. And as we are in the habit of doing, we'd like to start with a poll question. And if you would please participate by giving us your opinion. The first question is, how long since coordination was checked or updated in facilities that you're familiar with? And clearly it's not a right or wrong situation, it's strictly your experience. Just look at some feedback from the audience and trying to get a perspective on how fresh the topic is in general. The webinar is being recorded. The video will be posted to the website, and you'll receive an email including the attendance certificate when we post the video to the website. So it looks like we have a quorum. Let's see how people weighed in on this. Okay, so it looks like it's pretty well split. You might say, Jim, we had a coordination study done when the plant was first designed. Why do we have to do another one? And the question is, as things change, there's a tendency for operations or maintenance people to tweak things, or other elements in the system could change, and so consequently there could be changes that weren't accommodated by your first study. So just saying. So the second question is, has your facility experienced transformer or other equipment failures due to improper coordination? This kind of goes to the heart of what we want to talk about today. Frequently, the transformer is probably one of the most expensive elements in the system, and right behind that are large motors, and it's important that they be protected. So, interested in feedback on this topic. And I'm frankly surprised how often people respond in the positive. So it looks like we have a quorum. Let's see how people weighed in. Okay, so a few and some maybes. Fair enough. Thank you for participating. Let's jump into the show here. So we have this divided into four parts. Today we're going to cover the basic concepts and specifically get into detail about what TCC curves are all about. Next week we'll be going into fuse protection and the NEC guidance as far as coordinating with fuses. Part 3 we'll be doing low voltage power circuit breakers and multi-decay circuit breakers along with the NEC guidance that's relatively recent. And in the part 4 we'll be talking about relays, ground protection systems, and generator protection. So make sure you attend all three if you get a chance. Okay, so real briefly, coordination, the purpose is to protect the system and increase the reliability and minimize the chance of equipment damage with a process that we call, or is referred to as, selective coordination. And basically it determines the system's optimum device settings to protect the components and at the same time reduce the amount of system that gets de-energized once we've isolated the fault. So the example of this, or the one line that I use to represent this, is a typical radial system that if for some reason we get a fault on a remote bus down here on the left corner, well, that fault current can be felt by 3 different protective devices: the feeder breaker, the main breaker on the distribution panel, and then the primary fusing for the whole plant. Now, any one of those devices could detect the fault and be tripped. If the fuse were to open, we'd lose the whole plant. If the main breaker were to open, we'd use or lose other systems that may or may not be important. So in the real world, we really want just the feeder breaker to isolate the fault. So how do we do that? How do we ensure that we do that? Oh, just a real quick, I'm going to keep an eye open on my question box, and as often as possible, question from Harold. Are we going deeper into difficulties with coordination of TM trip units during the series? Harold, we refer to this as introduction to protective device coordination. So frankly, there's not a great deal of depth. We're covering a broad topic, so I may or may not be able to get to specific questions like that. My apologies. So the point being, when we're trying to anticipate selective coordination or verify that we have that capability, the tool that we use to do that is called a time current characteristic curve. And these give us the ability to display the damage curves for loads, including transformers, motors, cables, and the like, energy supplies, generators, the protective devices themselves, and the shape of each of these elements is determined by the manufacturer. So consequently, the data sheet from the manufacturer includes the parameters that allow the EasyPower tools to plot the TCC curve. And again, we're talking time current characteristics. So in essence, over how much time will the system operate or will the element operate before it's damaged. Now the display is in a log-log format, which makes it a little bit more different from what graphs we're normally used to. And secondly, we have time on the vertical axis. So these are called inverse curves, which means the higher the current is, the current's on the horizontal axis. The higher the current is, the quicker the trip time. Now, the gray plot looks like a cricket bat or hockey stick, is a typical plot for a molded case circuit breaker. The element down here at the bottom is referred to as the instantaneous trip area, and then the area at the top is the thermomagnetic trip area. The thermal trip, not the magnet. So the magnetic is the trip settings for instantaneous trip. And you'll find that this vertical column ends up being a problem area when we're trying to do coordination and arc flash calculations. So something to look forward to there. The blue curve is a typical plot for a low voltage power circuit breaker. And again, it's adjustable, whereas the molded case circuit breaker usually is not adjustable in terms of trip settings and reaction times. Whereas the low voltage power circuit breaker can be adjusted at each one of these segments, and we'll talk more about that in week 3. And then the rust color plot ribbon, this is a fuse plot. Its thickness represents the manufacturer's, manufacturing distribution parameters, and we want to determine the worst case time for tripping, which is where the trip current on the vertical axis, we're going to calculate the short circuit current down on the horizontal axis and then plot the line up along the TCC curve, and where it intersects the right upper boundary of any plot, that's going to tell us the reaction time of that device. So let's go through one of these examples. Or let's say we've calculated the fault current on this if and when this bus faults to be 5,000 amps. So we plot a 5,000 amp line on the horizontal axis and plot it straight up so that it intersects each one of these curves. If the multi-case circuit breaker, since it operates properly to this 5,000 amp fault, it should trip and clear the circuitry in about 20 milliseconds according to the TCC intersection point. Now, if the same current is exposed to the low voltage power circuit breaker, then it would clear in 300 milliseconds, which is the intersection of this 5,000 amp red line with the upper right-hand boundary of the plot for the TCC curve on the low voltage power circuit breaker. Now, even though there's a transformer in the way, the 5,000 amps in the 280 volt or the 208 volt range will cause that fuse to trip where the 5,000 amp secondary current intersects the right-hand side of the fuse plot, which means it would trip in 80 seconds. So what we've been able to verify with this particular exercise is we have selective coordination for this particular load. And if it's the largest load on this bus, we know we have coordination for all other loads on the bus as well. Which brings me to a point of suggested exercise, and that is prove to yourself that if you coordinate for the largest load on any given bus, by default you're coordinating for the smaller loads on that same bus. Got another question popping up. Yeah, Eric, there will be a certificate of attendance sent out via email. Usually you'll get it early next week. Okay. So when we want to talk about protecting transformers, we need to worry about overloads at the normal operating current or the normal operating part of the system. There's potential for internal faults, through faults. We're going to be looking at only through fault damage, because if there's an internal fault, then the transformer's busted already, and so downstream protection won't serve any purpose. If you have internal fault, the transformer's already damaged. So we're going to be focusing on through faults. By definition, it's an external fault, external to the bushings on the transformer. It's important to understand that the secondary windings specifically see very high current. So a 5% impedance ratio means that we have roughly 20 times the full load current as measured on the secondary side. And so because heating and magnetic forces are a square function, that means we could potentially see as much as 400 times normal current on the secondary windings. So what's the problem with through fault damage? It potentially overheats the windings due to high current. Again, the I squared R calculation has the potential for producing mechanical damage due to magnetic forces. The windings inherently repel each other, and this is worse on a very high current surge. According to ANSI C57.109, transformer damage curves they give us the ability to have a transformer damage curve that defines the magnitude and duration of the through faults and the withstand current. And there's another version for dry transformers as well. And to look at, we're going to walk through the TCC plots in detail, so bear with me. One of the things I would point out is that, again, if you understand how to extract data from the TCC curves in EasyPower, you will be surprised how many questions you can answer that you never thought about asking in the past. So here we're plotting the 100% damage curve. In EasyPower, it's a plot of a dotted line and is based upon the capacity and then the impedance ratio of that curve of that transformer. The TCC plot also gives us a display of the full load current, and then down at the bottom, this little dot represents inrush. So these are important milestones. The full load current is something that we need to take advantage of as far as the capacity to get the money's worth, if you will, out of the transformer. But at the same time, it gives us a reference point for protection. The 100% damage curve, by definition, we don't want to have the curve exceeded, and the time element decreases the farther up in current value we go. As I mentioned before, the upper part of the plot is due to thermal damage, and so again, this is susceptible to winding insulation degradation and other degassing and other issues over the long term. And then mechanical damage is the system failure that we're looking to avoid in the high current section of the curve. And then again, for inrush, if we have primary protection on the transformer, it's susceptible to inrush current. So at no point do we want to have primary protection fall to the left of this inrush, because that means every time we turn the transformer on or energize it, it will trip the protective device. Now, I mentioned ANSI C57.109. It's the IEEE guide for liquid immersed transformers through fault current duration. And it gives us several different categories based upon size and ampacity, and defines a term called frequent fault. So in category 1, which are small, less than 500 kVA transformers, it's a term that doesn't exist, and you won't see any change in the TCC plot for frequent faults. However, for category 2, 3, and 4, we will see the curve modified, the plot modified to represent the ability to withstand a frequent fault exposure. These are cumulative, and so what it means is that a category 2 transformer should be designed to withstand a total of 10 excursions to the frequent fault level over the lifetime of the transformer. So that ends up looking like this. The frequent fault area is this offset down here at the bottom of the curve, which gives rise to the naming of this curve to be as the Z curve, but essentially it's an offset of the 100% damage curve by some amount, and as long as we don't exceed the 100% damage curve, we're allowed to have a frequent fault according to the category described in C57.109. So the conservative thing to do is to make sure our protection is based upon not exceeding the frequent fault curve, which ensures the potential or the downside of even coming close to 100% damage curve. Okay. I think that makes sense. Let me check on a question. That's a good question, Abrahima. And that is, in a solar power plant, inverters produce 3 harmonics or third harmonics that can increase the neutral ground current. So yes, for that reason, there can be a K factor that needs to be considered when we're looking at harmonic damage. And that's something that's actually considered in harmonic analysis. So what happens if Robert's asking, what happens if you exceed the number of frequent faults? You have the potential of having damaged, mechanical damage of the windings, because this area exposes the windings to mechanical damage as they repel each other. And so what happens on the 11th excursion, it may not cause a problem, but the manufacturer usually doesn't guarantee that it's going to work to that point. So again, it's a conservative estimate. As long as you're not exceeding the 100% damage curve, the transformer should be able to survive that number of frequent faults defined in the category. So that's a requirement for the design. If you've exceeded it, then I'm not a lawyer, but I'm thinking that the transformer manufacturer is going to say, hey, you're on your own dime. Okay. Did I have a... Now there's an interesting phenomena on current rating or current alignment between a primary and secondary in a delta Y transformer. And that's because the per unit value seen by winding on the primary side is not in the same ratio as seen by the secondary winding. And so winding damage on through faults is a function of winding through any one current through any one winding. So we must adjust the damage curve for primary protection due to that compensate for that difference. What it amounts to is this. If we have a delta Y transformer where the primary is in a delta configuration and the secondary is in a Y configuration, for a three-phase bolted fault, the 1 per unit value correlates to a 1 per unit value on the phases on the secondary for normal full load current. However, if we have a single line to ground fault on the secondary, we have primary protection that we think we want to protect ourselves from that ground fault eventuality, we need to make it sensitive, derated by 58%. So you'll see that when we get into analyzing for single line to ground faults. So ignoring load current, the primary relay or fuse will see only 58% of the per unit current in the secondary winding for ground faults that are applied or protected by primary protection. And so what this amounts to is that there's an offset in the TCC plots, and so this is ignored in a three-phase fault, but if we have a single line to ground fault, then our primary protection needs to not be exceeded and not allow the current to exceed above this 58% derated curve. This only applies to primary protection, and it only applies to line to ground faults. So how does this change the TCC? So let me kind of jump into EasyPower and show you what this looks like compared upon different ground current. Now, all this is also impacted by the definition of grounding in our system. So here I have 3 different transformers. One has a hard ground, one has no ground on the neutral, and one has a resistance on the neutral leg to ground. So if we go into coordination, let me see if I got an example here. If we look at the hard ground, TCC, we can see that a three-phase bolted fault, let me go to three-phase. A three-phase bolted fault will draw 37,976 amps per phase, and our fuse on the primary side will protect it. And you'll notice here on our primary fusing, we are to the right side of the inrush point. One thing can be said, for a three-phase bolted fault, we have a lot of capacity of the transformer that's not being used. So in some cases, I may want to increase my transformer protection to allow better use of the capacity. Again, there's a trade-off based upon that and the potential of exceeding a damage curve. And that's for a three-phase bolted fault. If we check on a single-phase line to ground fault, now our fuse protection needs to be take into account this offset, which is the solid line, and consequently, if I'm relying on my fuse on the primary side, I need to make sure I'm clearing that primary fault line, the plot. So again, we're looking at the 480 volt range, and we're assuming that we want protection per phase to be more sensitive than a single line to ground on the secondary. Excuse me, on the delta Y transformer. Okay, that brought up a lot of questions. Oh, sorry, audio's having issues. Yeah, so Harold's saying he uses harmonic frequency mitigation, which is the way to go with VFDs and photovoltaic systems. And we got that one. And so William's asking, does grounding prevention of frequent fault become an issue? Oh, that's a good question. In general, I guess, because of the nature of the protection, if we're using fuses, it's going to slope such that the frequent fault's not going to be exceeded for a single line to ground fault. On the other hand, if I was using a relay or a breaker, there may be that potential. So let's go back and look at some other transformers. This is what I meant by asking questions or answering questions you didn't know you could ask. So let's look at well, I got this plotted out. So we got a high resistance ground on our neutral. Now you notice there's no second curve. There's no single line to ground fault curve or derating. And that's because the fault current is maximum on a single line to ground fault is limited to 100 amps. Well, that's down here in the mud. And in this particular case, we're only getting 2 amps on the 208 volt or 480 volt range for this particular transformer. So inherently, it limits the amount of damage to the transformer, and that you don't need to worry about it. And then finally, if we look at ungrounded, now this is a little bit variable on, now again, because there's no ground current, because there's no grounding in the system, there could be grounds in other parts of our system. And so in a larger exposure, we may see ground current. And sometimes that depends upon the amount of available ground current on a single line to ground coming from the utility. So be aware if you're just looking on local protection, you'd want to consider faults, a single line to ground fault on a wider scope. Okay. Yeah, just for what it's worth, if we look at a single line to ground fault and show all three phases, it gives us a better ability to envision what's going on. So if I want to go back to my, say, hard ground, and look at all three phases. For a single line to ground, I got two phases that have exceeding current, and then on the secondary side, a very high current exposure. Anyway, I digress. Any questions on frequent faults, ground protection, or single line to ground fault plotting? Good. Okay, that brings us to max settings for according to the NEC, we can have protection on the primary or the secondary, and there's a different curve for less than 1,000 volts. But if we have the primary over 1,000, and then two categories for the secondary, based upon using breakers, relays, or fuses, this gives us a reference to the maximum percentage of full load current that we can protect that transformer to. Now that in itself sounds a little confusing, so let's look at what we're talking about. And I want to look at, I think, my 300% curve. Okay, so what we're looking at is protection for this category 2 transformer. Category 2 is going to be 1,000 kVA and 6%, which puts us 6% or less, and 1,000 kVA and over 1,000 primary, I think less than 1,000 secondary. So let's see what does that for us. Yeah. Let's go to coordination. Let's see if I've done it. I have not. Okay, and this is something that comes up frequently when someone's first getting used to TCC curves. If we go by what the category rating is, we should have a fuse that the maximum sizing on the fuse is 300% of the full load current. Well, on the 480 volt range, our full load current is expected to be 1263. Our primary is where we have this fuse set up. So let's look at the primary. Let's set this primary bus as the reference point. It shifts all the curves to the left. Now our full load current, if I'm looking down here at the bottom of the screen, I put my cursor over the full load current is calculated to be approximately 45 amps. 45 amps times 300% would be 120. If I look at so right now, I have my fuse selected. If I look at the value of the fuse, it's a 50E, which one would think is 50 amps. I don't know about that. I'm looking at the setting down at the bottom of the screen, and it will trip at 127 amps, which is roughly three times my 41 amps would be 120. So it's close. NEC tells me I could set this kind of protection up for the transformer, but that while it takes a good portion of the capacity of the transformer available for use, if I don't have good secondary protection, I have exposure, at least on this upper area, for long-term loads. My point being, I probably need to be a little bit more conservative, and EasyPower allows me to pick another device from the device library from the same family, and it looks like a 40E size fuse would do a better job of protecting, and I'd have an issue with my inrush. So it's up to the engineer to decide whether we take a chance and make sure we get secondary coverage to cover the single line to ground fault, which if we put this here, my single line to ground according to this is going to trip the fuse protecting the primary. But I still have a large exposure to lower current, and frankly, I'd be curious how the philosophy that the audience would take as far as secondary protection. So the point I'm trying to make, even though the NEC tells me I can use a fuse as large as this, does my system really protect itself for lower faults, and what's the possibility of those lower faults occurring that I need to be aware of? So let's okay. So I don't see anybody freaking out at that. Okay, so the part that surprises some of us is when we pick a fuse, in this case 50 amps, that it 50 amps is only part of the story as far as the protection of a circuit. So if I really wanted 100% protection, I'd probably have to go with something smaller even than a 40 amp fuse. It just surprises me how frequently that comes up. All right, let's move on. Any questions about that? Okay, so the transformer inrush, the primary current must be able to ride through the inrush exposure. So in terms of my primary protection, I want to have it up and to the right of the inrush plot. Now it's hard to calculate because it is high in harmonic content, and these values, assuming defaults of 8 to 10 times the full load current for 1/10 of a second, is controlled by the settings in the device the transformer setup, plot setup, the TCC tab. And they can be adjusted. These are typical values, but your system, you may want to use a different one, especially if you know that it's going to be richer in harmonic content. Okay, I mentioned there's other TCC curves for other loads. Here's a typical motor plotted with its damage curve. This is referred to as actually the starting curve. The upper part is based upon the full load current that the motor presents. The bottom part is based upon the locked rotor current, and then the asymmetric tail is a glitch or a surge that's only in effect during the initial stall time, or while the voltage is first applied to the motor. And then this offset is the acceleration time to go from one stage to the other. And if you look at the starting current for most motors, they're pretty dramatic between the locked rotor current stage and the full load current stage. Right at the acceleration time, it'll swap between whatever the locked rotor rating is for the motor to the normal operations or full load current. So let's look at that real quick. Now you can see, if I expand this a little bit, you can see where these values are set up in the motor dialog box. We go to our temporary settings, look at the TCC. Here I'm using my locked motor multiplier to be at 6 times. We change that to an 8. And my asymmetric offset, my stall time, and my acceleration time, let's say, is 7 seconds. And apply. They may be something that I know the data from the manufacturer for this particular motor, or I'm trying to be more conservative. What it does, we want our protective device to be able to allow the full load current and the starting current under normal operations, but at the same time, this short stubby line is a thermal damage curve. So at no time do we want the motor current and time to exceed to the right of the short stubby line. So that's where motor circuit protectors come into play, because and overload systems come into play because they give us the ability to distort the protection curve to exclude certain areas and protect the motor at the same time. And we'll get into that when we get into molded case circuit breakers. And then finally, cables are plotted on a linear plot based upon the impedance and the voltage applied. And one of the things I didn't point out is when we plot these devices on the curve, there are tick marks that are supplied. Oh, so I don't have a protective device in the system, so it's not showing me the current on the plot. So let's fix that. And again, this falls into the category of answering questions you didn't know you could ask. So if we put a fuse in this system, and let's make it 75 amps. then the tool will show us, when we go to coordination, the tick marks that control the fuse plot. And if we fault this particular bus, I'm not showing tick marks because I didn't include tick marks on the one-line graphic. So here's my fuse. Here's my plot TCC curve. Here are my tick marks. And for some reason, I'm not getting a tick mark. So I need to go back and look at my setup. Okay, so that pretty much covers the basics of the TCC curves. Any questions before we wrap up? Certainly, if you have any questions for a specific allocation. So William's asking, is it allowable to use an HFD circuit breaker for motor protection versus an HCMP circuit breaker? That's more detailed than I can cover off the top of my head, but I'd be willing to play with it. It depends on what the plot looks like. And Harold offers, he tried to use fuses that are more bent curves, for instance, Merson or Ferrochamit or Trionic. I appreciate the feedback. Okay, that wraps up what we want to do. Appreciate everyone attending today. We will pick up the conversation next week, talking about fuses and the impact on series rating and how to coordinate with fuses. It ends up being an issue that there's a lot of confusion, and I think there's some misperceptions on how series rating fuses can help downstream systems. So we'll talk about that at the time. Thank you all for attending. Look forward to talking to you next week.